In this video, I introduce loss functions in recurrent neural network. To use a gradient descent method to train an RNN model, we need to define a loss function such as mean squared error or cross entropy, so that we can measure the difference between prediction and ground truth. The goal is to make the network prediction as close to the ground truth as possible. Our RNN model is a sequence-to-sequence model that maps the input sequence to an output sequence. For example, at step I, the model uses xi as input to predict the output of y. The goal is to make this prediction close to its corresponding ground truth. If we use mean squared error or cross entropy to define the loss function, the prediction generated by RNN model is a conditional probability of a ground truth given input xi. That is defined as a Bayesian probability. Say we have 6 data. We use a gradient descent method to train the model, make all the data close to their own targets. To use a gradient descent method to train the model, we need to calculate the gradient of loss function with respect to each model parameters. Here, the gradient is determined by all the data, not only by single data. That's why after we train the model, all the data moves close to their target, but not exactly on the target. That means the prediction generated by an RNN model is a conditional probability of a target for given input x. That is defined as a Bayesian probability. Let's see the mean squared error cost function. To define the mean squared error cost function, we first calculate the difference between the prediction and its corresponding ground truth. Here, M is a number of classes. This expectation is over the input x. So the ideal case is here is the ground truth. This desired output is this output is same as the ground truth. However, the actual prediction is a dense vector. So we need to show this prediction is a Bayesian probability. To do so, we suppose this P is a joint probability of input X and class C. Use the definition of Monte Carlo approximation. We can change this expectation to the integral. And then after some derivations, we can use 2 terms to express this cost function. Because the second term is no relation with the prediction, so only first term determines the cost function here. So for one of M problem at the minimum cost loss error, so the prediction is equal to this conditional probability, which is a Bayesian probability. Then next, let's see the cross entropy cost function. To do so, first we view the output and the labels as the probability distributions. So the binary cross entropy cost function defined as this. This 2 means the binary. This M is the number of classes, and this E is over the input X. So we expanded this binary 2 terms. So we have this expectation to express the loss function. So this loss function used to measure the probability distance. After some derivations, we have these 2 terms to express the loss function. Because the second term is no relation with the prediction, so only first term determines the loss. So at the minimum loss error, we have this prediction equal to this expectation. For one of m problem, this prediction equal to the conditional probability. That means the network prediction is a Bayesian probability. For more details, please check with this reference. Thank you.